Hello, everyone. I'm Placido Murcia, and today I'm going to give you an overview of the work carried out within the 6G-DISAC project, and specifically within Work Package 4, which is about resource allocation for ISAC and new distributed and cooperative sensing. So the presentation is structured into two main sections. The first one is about the basics of this work package. What are our figures, our objectives, our interaction with the broader 6G-DISAC project, and our achievements so far. Then the second part will dig a little bit deeper into the more technical part on the results for the three tasks that we have within this work package. So as I mentioned before, this work package is divided into three tasks. The first one is about design of efficient protocols for ISAC. The second one is about orchestration algorithms for distributed and cooperative communication, sensing, and computation. And finally, the third one is about spectrum management for optimized ISAC operations. In this regard, we have three deliverables containing the results of this work package. The first one is already available and online, more details on that later, while the next two ones are expected later in 2026. In terms of work package level objectives, we identify four key objectives. The first one is about a design of innovative distributed protocols that enable efficient ISAC, and this means fusing information that is being sensed by possibly a massive number of network nodes, which may be of different types, and we'll give more details on that later, and also exploiting the associated contextual information. The second goal is on developing goal-oriented resource allocation and orchestration schemes. Again, these schemes will exploit contextual information and allow for achieving certain applications such as computation offloading, over-the-air computation, and computing splitting. The third objective is about developing novel efficient spectrum management techniques. So these techniques are designed to allow energy consumption minimization, electromagnetic field exposure reduction, or in general efficient optimization of the communication parameters. Finally, the fourth goal is about distributed multi-radio access technologies sensing. This deals again with the fusion of sensing data, which may be collected from multiple heterogeneous sensors, which together allow to enhance the sensing of the target. Work Package 4 also relates to overall 6G-DISAC project level objectives, in particular three of them. The first one on designing sensing-aided wireless communication techniques, while the design of these techniques obviously includes the protocol aspect, but also the resource allocation aspect. Objective number 4 on development of resource allocation schemes and protocols for DISAC, which again exploit contextual information from a large number of heterogeneous nodes. And objective 5, developing and validating the 6G-DISAC architecture. Indeed, the design of the network architecture is tightly coupled with, for example, the protocol design, but also the resource allocation design, as well as the spectrum optimization. Here we have an overview of how Work Package 4 interacts with the other work packages within 6G-DISAC. Work Package 2, for instance, is dedicated to identifying use cases, metrics, and the DISAC architecture, which then is tightly coupled with the design of protocols and resource allocation algorithms. Then with Work Package 3, which is dedicated on defining the technical methods for sensing and communication in distributed settings. These methods and requirements are provided to Work Package 4, which in turn gives resources, protocols, and spectrum constraints. On the right-hand side, we have Work Package 5, which is about evaluation through proof of concepts, so demonstrators. In this case, hardware constraints and results are provided to Work Package 4, which in turn gives methods and protocols that are needed for such demonstrators. And finally, all results are provided to Work Package 6 for dissemination, exploitation, or standardization. Here is a small overview of the achievements that Work Package 4 has managed to get so far. In the first task on designing efficient protocols, we have provided 8 protocols that target distributed sensing with heterogeneous devices, including both connected users to the network, but also non-connected targets. Again, more details on that later. Then we have protocols that enable RIS-empowered sensing, dynamic beam searching, federated learning of sensing devices, or sensing with semantic waveforms. In the second task on orchestration algorithms for distributed and cooperative communication, we have proposed 5 algorithmic solutions that tackle multi-sensor and multimodal systems. And we have 4 detailed analyses of the optimized trade-offs that exist between computing, communication, and sensing resources. And in task 4.3 on spectrum management, we have some preliminary results that I will detail later on dynamic spectrum access, which is tailored for lightweight devices. So far, we have also kept a close interaction with Work Package 2 and 3, since the network protocols designed here are specific for supporting Work Package 3 algorithmic approaches and are also integrated within the DISAC architecture, which is developed in Work Package 2. All right, this concludes the first part of the presentation, and now in the second part, we will dig a little bit deeper into the technical details of such solutions. First, let me briefly describe the foundations of this work package. In this work package, we deal with network protocols. That means a set of rules and conventions that define how data is transmitted and received across the network. And this includes the format, the timing, the sequencing, and so on. Then we deal with orchestration algorithms, which are a way to coordinate, manage, and automate the arrangement and interaction of multiple components, multiple tasks, multiple services within an overall system. Here we have a special focus on resources that are dealing with computation, communication, and sensing. We also deal with spectrum management, which means efficiently allocating, assigning, and utilizing the radio frequency spectrum. This includes support for different radio access technologies, which may range from sub-6 GHz to millimeter wave or even sub-terahertz, and a spectrum allocation which is dynamic. So it evolves over time. It's not static, and it depends on the underlying channel conditions, but also instantaneous requirements. I mentioned several times that we deal with heterogeneous devices. So what we mean here is wireless entities that may have various communication, sensing, computation capabilities, but also storage availability or power consumption, power budget. We deal with distributed schemes, which means multiple independent nodes coordinate and communicate to achieve one common sensing or communication goal, or both. For example, think about positioning or maximization of the system rate. We also deal with semi-distributed schemes where, just to give an example, the sensing data may be collected in distributed fusion centers. Associated to distributed schemes is distributed optimization, which means starting from a large and complex optimization problem, which may be a communication, sensing, or both, and dividing it into simpler and smaller subproblems, which are solved by the multiple distributed nodes. Such approach, the DISAC approach, brings specific benefits. For example, utilizing the resources of the network in a very efficient way. For example, we target specifically the minimization of the overall energy consumption. Clearly, the diversity brings gains both in communication and sensing, the spatial diversity. We are able to support many different heterogeneous devices under the same framework, and we allow for sensing of both active users connected to the network as well as passive targets that are not connected to the network. However, the DISAC approach also brings some specific challenges. For example, the need to keep strict synchronization and coordination among the distributed nodes, an extra latency and overhead to again, to this coordination, and inherent trade-offs for dynamic management of computing, communication, and sensing resources, which needs to be addressed and optimized. Having given the foundations of Work Package 4, we can now move to the specific results of each of the three tasks. The first task, as a reminder, is on the design of efficient protocols for ISAC. One of the main aspects covered here is distributed sensing for non-connected target versus connected users. And this includes the signal design in time, frequency, and space. As you can see on the right-hand side, we detail the message exchange between distributed entities. So we start from a sensing client that initiates a sensing request in its field of view by contacting the SEMF, the sensing management function, which is then tasked with selecting appropriate sensing transmitters and receivers, including the case of UEs. The sensing is then started by the selected transmitters and receivers, which may include the presence of a sensing target, so an object that is not connected to the network. The measurement reports are then provided to the local sensing processing functions, which are effectively distributed intelligence in the network, which provides some initial local processing on the data, the result of which is then provided to the central sensing processing function, which is a unique entity in the network, which provides fusion of these local sensing processing. The result of that is then sent finally again to the SEMF and to the sensing client. It's important to note here that traditional centralized processing may fail in complex or noisy environment because it leads to large overhead and finally poor sensing. Thanks to the distributed approach, we are able to increase the accuracy of the sensing with less overhead thanks to the collaboration, so the parallel handling of the data. Another important aspect here is sensing with heterogeneous devices, as I mentioned before. And here we provide a specific notable example of RISs, reconfigurable intelligent surfaces. On the right-hand side, we detail the network connections between distributed base stations, distributed sensing receivers and transmitters, and also sensing targets with the aid of distributed RISs. In this case, we account for both when the RIS is controlled by the network, so effectively the network instructs the device on its optimized configuration, but also the case of autonomous devices, so devices that have some local sensing processing function themselves and can exploit the local channel knowledge to optimize their own configuration. On the left-hand side, we also detail specific interfaces to allow full integration of such devices into both 3GPP and O-RAN architectures. In the second task, the main results include cooperative and distributed multi-sensor and multimodal systems. Here we detail a specific example of optimized resource allocation for passive sensing in a dense RIS-enabled millimeter wave environment. So as you can see on the right-hand side, we have a system that is designed to provide sensing of a passive target that is not connected to the network with the aid of a sensing dual beam RIS. On the left-hand side, you see that we clearly detail the difference between sequential and concurrent ISAC modes. So in the first case, the sensing and the communication happen in consecutive time instance, while in the second case, they happen concurrently. Of course, concurrently means that there is a more efficient utilization of the network resources. However, this comes with specific challenges. For example, the sensing may happen on side lobes, and such a fact needs to be managed. Details on this implementation can be found in the deliverable, which is linked here at the bottom of the slide. Another important example includes opportunistic UE localization without any disruption to the communication. So on the right-hand side, we show a system where basically we have a communication system on the left-hand side, which is optimized on its own, which includes a base station, an RIS, and a user equipment. On the right-hand side, we identify an AI agent dubbed as Coloris, which essentially takes into as input only a copy of the RIS configuration and exploits that to estimate the position of the user. So it provides no disruption whatsoever to the communication part, no overhead, and still manages to extract sensing information. Finally, we dig deeply into the trade-offs that are inherent in ISAC systems, especially when we talk about dynamic management of computing, communication, and sensing resources. Indeed, finding the optimal balance between communication capacity and sensing performance is not obvious and requires optimization. In particular, here we identify a dynamic spectrum allocation strategy across OFDM subcarriers that is able to optimize the resolution ambiguity trade-off. And again, more details are available in the deliverable. Finally, we can move to results on the third task, which is about spectrum management for optimized ISAC operations. Here, the main aspects covered are the support for different radio access technologies, ranging from sub-6 GHz to millimeter wave, and a dynamic spectrum sharing method, which means a spectrum allocation which is not fixed in time, but is dynamically updated depending on instantaneous requirements. The particular example that we put forward here is on a network of distributed lightweight devices that have shared spectrum resource, each one of them having low computational capabilities. The method proposed here allows all devices to learn online the spectrum access patterns by exploiting sparse recurrent multi-agent deep reinforcement learning framework, where the network is gradually pruned and harmonic alliity sparsity scheduler is exploited to comply with the computational capability constraints. This concludes my overview of the main results obtained so far by Work Package 4. I thank you all for your attention, and I hope to see you soon either on our project website with news and public deliverables or on social media. Thank you.